Hello, everybody. Welcome back to our ExoLife Hangout that we are now doing twice a month. And today we're going to be looking into the question of, are we ever going to find life on Mars? And what's more, do we really want to? So we're going to explore some of these issues today. And we've got a great guest here who studies these things. Is going to talk to us about an astrobiologist who I will introduce in just a moment. But before I do, I want to take an opportunity and tell you about something that's happening here in Deep Astronomy I'm a little bit excited about. This month, we are teaming up with the Great Courses Plus. They are sponsoring the Deep Astronomy channel. And I wanted to let you know about some really interesting online learning material that they've produced that I think is pretty great. Now, this is a good matchup, I think, because I know a lot of the people who watch these Hangouts also like to they watch lectures on other channels and by other institutions. And the Great Courses Plus site has been around for quite a while. I was a customer in the mid-2000s, and I bought several of their courses from different professors, in particular Sean Carroll's on dark matter and dark energy, and I really learned a lot, and I still use that course in writing my scripts for Deep Astronomy videos. So what's great is they put all this stuff online now, and they are what I think you guys would be most interested in, and what I'd like to point out is if you go to the link that I have in the description box, thegreatcourses.com/deepastronomy, you'll get a month free of all their courses, and that gives you an opportunity to see some of the material that they've got. And of interest to you guys, and it's related to this Hangout, is they have an entire course of about 20 lectures on exoplanets, how we find them, and what the science behind exoplanets are. And there's also another one called Life in the Universe, which is relevant to what we're talking about as well. And I've been watching some of those lectures already, and they've got a lot of great topics, not the least of which is one on Mars itself, what the history of Mars is like, and could it have ever had life. So I would encourage you guys to check it out. If you click on the link in the description box, you're also helping support Deep Astronomy. So and you'll get a free month's trial subscription. So they have a lot of different offerings. Please check them out, and I want to thank them for working with me for the month of October to do that. Okay, so without any more ado, let me get rid of this and pull these guys up. This is the ExoLife Brady Bunch view of everybody that we've got. In the bottom row there is my co-host Dr. Jeff Kuhn. He joins us each ExoLife Hangout from the University of Hawaii. He's a member of the Planets Foundation. Hi, Jeff. Welcome.
Good morning.
Good. It's good to see you again. We're going to be. You ready to talk about Mars?
Absolutely.
Absolutely. Look at him. He's just really just chomping at the bit there. He's ready to go. Also in the upper right is Kevin Lewis. He helps put these together. He's also with the Planets Foundation. He arranges these Hangouts each time. So it's good to see you again, Kevin. Welcome. And
hello, Tony.
He's also going to be helping me with the social media aspect of this Hangout. If you are on YouTube, if you are on Twitter, if you are on Facebook or Twitch, with them, please comment at us, ask us questions, and we will read them out to our guests. Already, the live chat's filling up really well, actually, on YouTube. So it's really good to see you guys, and we'll read those comments out and read them as we progress. So today we're going to be discussing life on Mars. It's a question we all been asking for quite a while. It's been in the headlines. We haven't found any yet, but my guest today is Dr. Kai Finster. He is an astrobiologist at Aarhus University in Denmark. Welcome, Kai.
Yeah, welcome. Good evening.
Yes, he's joining us from his home in Denmark, so thank you very much for taking time out. It is late in the evening there, and I want to thank you very much for taking time out to talk with us and let us know what's going on with Mars. So tell us a little bit about yourself. What do you study, and give us some background on what you're doing. That was my dog.
Yeah, my profession is I'm a microbiologist, and I've been doing microbiology of extremophiles, organisms that live in extreme environments on Earth. And for about 15 years, I got involved in Mars projects at our university. In the first place, it was just investigating the formation of a soil that has been used as a Mars analog soil in simulation experiments. And we tried to understand how these soils form and if there was bacterial involvement in that. And ever since, I have been studying the survival of microbial communities in Mars simulation facilities. And recently,
Microbial communities in what? I'm sorry.
we have a Mars simulation facility. So we it was in the permafrost soil, which is also an extreme environment. So we've tried to figure out which parts of this community survive simulated Martian conditions. And then we also, what I'm interested in now is the effect of abraded soil erosion processes on reactivity of soils, in particular minerals that are analogs to Martian minerals. So we try to figure out if the erosion process could have an effect on survival of organisms and persistence of organic matter in a Martian environment. I can explain that in more detail later. But
well, okay, good. But I want to go back a little bit because I want to talk a little bit about what extremophiles are. Give us an idea. What for those of you, the audience here, they're pretty science literate. They ask great questions. But for those who might not know, what are extremophiles?
Yeah, I mean,
and how do you become one? No.
Yeah, how do you become an extremophile? Yeah, I mean, the word extremophile is a bit anthropocentric. I mean, it's taking, we look at ourselves and everything that is very much different from ourselves and requires different conditions for life, we consider as an extremophile. For example, if we find an organism that lives at very high temperatures, let's say about 60, 70 degrees, we would consider this as an extremophile, because if we were put in water of 60 or 70, and I'm talking about not Fahrenheit, it's Celsius, so you have to recalculate it. I don't know how many Fahrenheit that is, but it's pretty hot.
Yes.
It would burn, and you would not be very happy to live under these
150 or so degrees or something like
that. Yeah,
so
it's not nice.
You're right.
It's pretty hot. So this would be there are many organisms, but in particular the microorganisms that can live under these conditions and that only live under these conditions. If you take them to temperatures that we like, so let's say 80 Fahrenheit, is that okay? Is that a nice temperature?
It is to me. I live in Florida, and that's pretty much that all the time here. So
for you, that would be the perfect temperature to live in. And so that's the definition of an extremophile is always with in relation to what we consider as a nice and good environment for organisms like ourselves to live in.
Now, we study extremophiles for a reason. I mean, it's amazing that, first of all, they exist. I mean, they sorry, I was reading Kevin's chat there. They're amazing creatures, actually. They can live in these environments that are very extreme, or that's why they get their name.
Yeah, but if you ask an extremophile, and they looked at us, they would say, "Oh, it's an amazing character that can live at only 30."
Exactly right. It depends on your point of view. As with everything, it's all relative. So
it's relative.
Yeah. So to an extremophile, I'm an extremophile because I'm living in this 80-degree. Oh my God, how do you do it? Climate, and they're like, but give me a good old 150-degree boiling water environment any day, right? So.
Yeah,
but it's important when you're studying life in the universe, because there are other environments besides Central Florida in the summer or Denmark in the winter.
Yeah,
we need to look at the wide range of things that are out there. So
I mean, when we look into Mars, we can see what are the conditions on the Martian surface, for example, and we find we have a harsh radiation climate since we have no atmosphere, so a very, very thin atmosphere. UV radiation hits it. It's very dry. The temperature is changing a lot, so very relatively mild during the daytime at the equator, but very, very cold during the nights. And if we want to figure out whether organisms can live there, we have to find organisms which live on Earth under these conditions. And in order to find these bacteria, or these organisms, we usually have to study bacteria, because these are the organisms that usually can live under these extreme conditions. And then, because for us the conditions are extreme, we study extremophiles. That's why we did experiments with permafrost in our simulation experiment, because the soil on Mars, if you just dig a tiny bit underneath the very, very surface, is permafrost. It has been frozen for billions of years. And we have nothing like this on Earth. I mean, the oldest permafrost, at least in the northern hemisphere, is maybe 4 million years old. so a factor of 1,000 different.
And it's thawing. I'm hearing too, but
Yeah, and it's
that's
thawing
another
also.
topic for
Yeah,
another day.
yeah. So, but still, I mean, this is an environment where it's permanently cold. There you have problems in there's not so much access to water. It's a relatively dry environment. So some of these conditions that we find in permafrost are comparable to conditions on Mars. I mean, there's nothing on Earth that is like Mars. There are environments that have similarities to Mars, but that's the closest we can get is by finding organisms that live under extreme conditions. It could be the dry deserts of the Antarctica valleys, or where we also have very dry and very cold conditions, very little nutrients and so on. So these could be comparable environments.
Okay, I have a question for you. How do you feel about the people that might say, well, okay, so we look at extremophiles and that gives us an idea of the range of extremes that life can live in, but maybe that's a bias. Maybe under a different evolutionary process, conditions, the life that could exist in Mars would be remarkably different. And I have an example. I'm thinking about some of the comments made about the Viking experiments 30 years ago. So what do you think of that? Do you think it's unlikely that evolution?
Life adapts to the conditions. If we compare life today with life as it was 4 billion years ago when it originated, it was, I mean, the building blocks were the same. It was cellular life. It was life that uses a DNA code. It used proteins to do the work and so on. So in that respect, life was very similar. But then it has changed a lot. And it's a mutual process. So life changes, but it also changes its environment. So the Earth at that time looked different, not only because geological changes happened, but also because life evolved, and life has a large impact on the environment. And if you imagine that there was an origin of life on Mars, of course, life on Mars either got extinct or it had to adapt to the conditions. So I guess it would have the same features as life on Earth, but it would have evolved differently because the environment is different.
So can you tell us a little bit about let's go back to early Mars, what Mars might have been like in the past compared to what it is now. We know it's quite different now. In fact, we had Robert Zubrin on a couple of months ago, and he was basically saying this whole idea of planetary protection is nonsense. Mars basically is sterile on the surface because of the radiation hitting it and things like that. So an extremophile that lived there today would have to probably live under the surface or maybe somewhere else. And we'll talk about the conditions now in just a minute. But I want to go back to Mars of the past. Was it more hospitable compared to what we say? When I say hospitable, I mean more Earth-like or more conducive to life. And does that question even make sense? What is more conducive to life?
Yeah, I mean, that's how it looks like. It seems that some of the minerals that we find on Mars, I'm not a geologist, but what I read in the literature is that this can only form in aqueous conditions. So there must have been surface water.
So you need water.
You need water, and there was water on the surface. Also, the Curiosity rover showed that we find these pebbles, which apparently also have eroded in a specific way, as it only can happen in water. We have sediments, so sediments can only form in water. So at least what I learned from reading the literature and from geologists and geophysics talking about the evolution of Mars, it seems to me very clear. Also, the riverbeds that you can see, that there was water on the surface of Mars. So at least it was much wetter than it was today. And this is a major difference compared to life to the conditions as we find them on Mars today. If that means that planetary protection doesn't make sense, I don't know. I have other.
Oh, that was just his comment. He thought this whole business of getting bent out of shape about being protective of Mars was nonsense. And
we know from Earth that there's plenty of life in the subsurface of Earth, and the subsurface of Mars is also different. And you don't need to dig very deep in order to have a relatively protected environment.
Okay, so back in the day, Mars probably had some water. There's evidence all around that says it was probably liquid water flowing on the surface. What about the atmosphere? Now, I think it's MAVEN that's currently in orbit around Mars that is measuring its atmosphere, its upper atmosphere, and I think that's the probe that found that the atmosphere is actually being blown away. It's actually losing atmosphere. Mars is.
I mean,
So
Mars ran into a problem when it lost its magnetic field.
right.
So this is a very important function.
So okay, so back in the day, it had a magnetic field too, right? That
Yeah,
would have
well,
been
it seems to be
hugely
so
important.
when you look into the iron-containing minerals, that you could see that they still have the signature of a magnetic field. So Mars had a core, and that was like the core on Earth, a kind of dynamo that generated the magnetic field, as I understand it.
It was probably more active geologically too.
Much more active.
Yeah.
You have the massive volcanoes, so it also tells you that there was it was a very active planet at the time.
Okay, so
very different.
So what do we know? So what does that tell us maybe about its atmosphere in the past? Would it have been more? Would it have been thicker?
I think, it must have been much thicker. It contained much more CO2 in the atmosphere, which it protects. I mean, what is important for life on Earth, at least life on continents, is that we have oxygen in the atmosphere, so we have an ozone layer that is protecting us against UV, at least a very shortwave UV radiation, UVC radiation, and this is a condition that's very important for colonization of the land masses. So it's not just that we have a thick atmosphere, but we also need an atmosphere that shields us from UV radiation. Okay. That's a big problem on Mars today.
Okay, but that would be for us. And now your comment early in the hangout got me to thinking. To an extremophile, I'm an extremophile. So how do we know what the proper conditions for life are? And Jeff has said this many times in many hangouts before. He goes, look, we're going to find stuff.
Too important to me. It's more the experiments that we do, the way how we look for it, the way how we view life on Earth, how we try to take what we learn from life on Earth to Mars when we look for it. This is more I think I would say that the process, to me, it's much more important than the final goal. Of course, I mean, we are motivated by the idea that there must be life somewhere else in the universe, and Mars is the closest place where we could look for it.
The journey, not the destination.
Sorry?
The journey, not the destination.
Exactly. Yeah. I mean, we have learned so much just by the type of experiments that we do. When you consider how naive people were just only 60 years ago when they designed the Viking mission. I mean, people were very much convinced that they just had to dig a bit in the surface and they would probably find life there.
Well, I've been reading about I was around when the Viking mission returned its results, and there are people now that say, well, if there was life there, when they poured water on the soil, they killed it, they drowned it, because it's likely that if you had the life there, that maybe it was based on hydrogen peroxide or something that allowed this chemistry to go on at lower temperatures, as you were saying, than current temperatures.
Yeah, I mean, we do some experiments at the moment where we do, it's a very simple experiments. We just take different minerals, basalt or some quartz-like minerals, and we take them in and we erode it. So what we do, we simulate erosion, wind-driven erosion on Mars in a Martian atmosphere. When we take these minerals and under oxygen-free conditions, put them in water and inoculate them into bacteria, even the very harsh ones like Deinococcus radiodurans, which is famous for its resistance to radiation, they get killed. So they die off, and within 24 hours, we have no living cells left.
But again, it could be that we're looking at an evolutionary track under Earth conditions.
Exactly.
It's striking to me that life is much more robust than we give it credit for. I mean, we as what chemistry blobs of bigger chunks of meat are not nearly as robust as other forms of life that we find, and that's what you're seeing with extremophiles. So I
think
find
we give it plenty of credit. We give life plenty of credit for being robust.
Well, okay, but when people say Mars is a sterile environment, I think if life ever emerged on Mars, And okay, so the atmosphere goes away, and UV radiation is a really hard thing for most forms of chemistry. It retreats into the soil, or like National Geographic says, it goes down into the lava tubes. But it's so robust, and the meaning of life is to expand into any available niche, that I think my gut feeling, and I'm of course not an exobiologist but a physicist, is that as if it ever was there, it's still there, but we just haven't rooted it out of the soil.
I mean, this is maybe one of the problems with planetary protection, that they prevent the people that are involved in planetary protection. They prevent people from going to the places that may be the most interesting. So we were handicapped by the fact that it was difficult to land on Mars, but now with the sky crane and these equipment, it's much easier. And it's not easy, but it's feasible to land your equipment in environments that would be interesting to investigate. But these in interesting environments, they are protected by planetary protection. So maybe the most interesting environments, we cannot probe them, we cannot study them.
Is that true? I mean, there's already like set up little wildlife refuges already. We can't.
Yeah, there is. Yeah.
Yeah, I guess I
So,
remember.
I mean, you cannot go everywhere. So there are some, and this would maybe be the places where you should go in order to find life.
Well, so answer our question for this hangout for us, Kai. Are we ever going to find life on Mars then? What's your opinion? I mean, life, not evidence of past life. Are we going to find a live life now?
Well, I agree with Jeff. If it ever evolved on Mars, we'll find it. We just have to go to the right spots.
Okay, but you're not being definitive. You're saying if it evolved on Mars.
If you're not lucky on Earth, you could find spots where there's very, very little life. You would have a hard time to find it. So even on Earth, where life is everywhere, you can find spots where your techniques are not sensitive enough to detect it. So I think we have to go to the right spots. It doesn't make sense to look in places where it's very unlikely that we can find it. I think these lava tubes, as you said, they could be great places to look for life. It's technically quite demanding to go in there, but that would be spots that were, I guess, that were really.
Okay, well, let's explore that a little bit more. So you're saying that there are places we can't go because planetary protection is saying these are no-go zones, and you really want to go there to see if there's any life. But you're also saying that we're limited by our techniques, and right now our techniques are pretty much rovers, aren't they?
Yeah.
They come and they poke and they prod the dirt, they drill, they break open rocks, and they do things to the soil and to the surface. Do you think that's enough, or what would you like to see on Mars to help you really? Let's say you could go to those lava tubes. What would you like to have? Would you like a person going there, or do you what a specially designed rover?
I think we should work on robots.
So you're saying rovers are the way to go?
Yeah,
robots,
not people. I mean, that's why it's so costly to send people. You can use, if you use that money to I mean, robot technology is evolving a lot, and I would go for intelligent machines rather than sending people there.
So let me, and maybe Jeff, you know too, because I can't remember all the different probes and rovers that have gone down. But since Viking, which was specifically had experiments to look for life, there has been. Have the rovers had experiments on them that tested? I think Curiosity didn't it? Had a.
I'm sure Kai knows better. I think that I just keep coming back to the sort of retrospective on Viking, which was the first real attempt, and I think we have this sort of preconception of what life was from that, and it could very well be that it's just. You dump water on it and it's exactly the wrong thing to do, because it's based on, I'm fascinated by this idea that life could have this hydrogen peroxide base to it. Do you have have you thought about that? Or, I mean, because there is an example of a beetle on the Earth that actually creates hydrogen peroxide and defends itself.
We use hydrogen peroxide to kill off microbes.
Right. And
so
that's my point.
But the hydrogen peroxide is when you respire. That's one of the intermediates when oxygen gets reduced into water. You form hydrogen peroxide, and your cell is really busy in controlling that. The same way when you do photosynthesis, you go from water to oxygen via hydrogen peroxide. So cells are used to handle that. We have sophisticated enzymes that detoxify hydrogen peroxide.
But there's a I think it's called the bombardier beetle.
Yeah, but they don't live on that. They use it as a toxic compound.
Yeah, exactly. But they can create it, and therefore the chemistry for
also.
Yeah.
So it's not so that it's regular. I mean, we form it all the time while we respire. We just control it. We have enzymes that control it, that keep track, and that we don't want to have it in contact with our with our cellular machinery, because it's so reactive.
Well, keeping to Jeff's point, then, how do you design an experiment that you're going to spend hundreds of millions of dollars on a rover type thing to send to Mars? How do you what is the best kind of experiment to design for this? Are you like, I mean, I don't know. It seems to me like what Jeff's suggesting with hydrogen peroxide based life forms is probably not as statistically possible as say something else might be. So how do you think about this when you're designing an experiment?
I mean, for hydrogen peroxide would be used as an electron acceptor in the same way it would be respired. So the organism that uses hydrogen peroxide instead of oxygen.
But I think the question is, do you have any ideas? So
here we are. Yeah, but how would you? What would be your ideal experiment to send to Mars?
What's a life signature that?
All things being equal, you don't know if there's life there. You don't even know what it's based on. What would you do? How would you think about designing an experiment to be as definitive as possible and to justify the money to send on a rover?
I mean, I worked as a microbial ecologist for many years, and in microbial ecology, we measure activity of microorganisms without knowing who's doing it. So we use, in a way, the Viking experiments were clever experiments. I mean, you can be criticized them for having used water, but they did what we would do to investigate activity. They used radio-labeled compounds. They used radio-labeled sugars and amino acids. We could use other compounds which are not organic based, but I would say that you have to go for redox chemistry, because no matter how the organism is organized, which enzymes it's using and so on, it has to have some energy conserving processes, and this is redox chemistry. So any experiment that would show that you have a redox chemical process going on, which could not go on under these conditions only chemically, but needs to have biological catalysis, would be a good experiment for me.
Okay. And this is all assuming, of course, you could go to the places that you would want to run this experiment on as well. All right, let's get to some questions here. We've got quite a few that Kevin's been putting up here. David Corvini, wonder, if we dig here, we say digging in the Earth. If we dig there, do we say we are digging in the Mars? I need Tony's opinion. No, I think Earth is a noun that describes the soil as well as our planet. But I think if you're digging on Mars, you're digging in Martian Earth. I guess that does sound kind of stupid.
Yeah.
I don't know.
So,
what do you guys say? I say, yeah, you're digging into Mars.
Yeah. It's fine.
I don't think you say the Mars.
The Mars. Well, we say digging in the Earth. We say that here, and that was the point.
Well, but I think you'd say Earth is special. Digging in Mars.
Earth is special. I'm special too, Jeff. I just wanted to say that
yes,
just so I could annoy you.
We're all special.
Yeah, we're all special, and we're special in the universe. So, upcycle electronics. Don't we find bacterial life deep in the soil here on Earth, as deep as we have ever gone?
I think we've gone down to 15 kilometers or so. And we didn't find life there. I think the deepest is about 2.5 or 3 kilometers. It depends on the temperature. When the temperature gets above 120 degrees, it's sterile.
What kind of bacteria did we find at 2 kilometers? And how did you find it? How do we find it?
We drill.
No. But how do we know that it's there? We petri dish and we
pick it up, and we can extract DNA from the samples. We can visualize cells by microscopy. There are different methods to do that. We can measure their metabolism by adding
Yeah.
different isotopes and see how they are transformed.
So at 15 kilometers, we don't detect life to a certain fractional population, right? I mean, if there were just 1 or 2 cells per cubic centimeter, you might not find them, I guess, huh? Yeah, or is life such that it would always proliferate in a way that you'd be able to find it?
I mean, there has not been 15 kilometers is too hot.
Temperature is too hot.
Yeah, it's too hot. I mean, when you can, what we know of, there was a report on life at I think it was 200 or 250 degrees. It was in the 80s, I remember, from Paris.
Yeah, above the boiling point of water.
Yeah, but that was at hydrothermal vents a couple of kilometers down.
So it's just high pressure, so it wasn't boiling, but life did exist above.
But it turned out that it was an artifact. People did some calculations, and they figured out that proteins are unstable at these temperatures. So
there's no life above the boiling point of water.
There is life. I think the record is about 130 degrees.
Where's it found?
It is one of the hydrothermal vents. I can't remember exactly the location.
But it's at high pressure, so the water's not boiling.
Pressure, yeah. It's an ion reducer. It's an archaea. Well, it's a special type of microorganism.
But it still has the same amino acid complement that everything on Earth has.
Yes, these archaea, they are quite special organisms. Yes. They have special cell walls and so, but they have the same type of DNA, proteins, and so on. They just have special protection.
You must get excited when you find life like that, don't you?
Yeah, it's pretty special.
Yeah.
So, now that you bring it, what did you say it was archaea? Say that again.
Archaea.
Yeah, archaea. It's well, we have microorganisms. We have two different lineages of microorganisms, and one is bacteria, what we call bacteria, and then we have another lineage which is called archaea.
And there's also what are eukaryotes? What are those?
Well, eukaryotes, these are types as we are. It's a special cell type.
Okay. It's
much more complicated cell type.
Okay, so I've made some videos in the past on life in the universe, and I got in trouble by calling bacteria and eukaryotes and all this stuff simple life, because a biologist will see, as I'm not a biologist will read my script or listen to my script, and they'll go, "What do you mean? Bacteria is not a simple form of life." Do you agree with that statement? Is it complex, bacteria?
Yeah, of course there's no simple life.
There is no such thing as simple. So I was going to ask you, what would be the simplest form of life that one could have?
I mean, I think, if I'm not, you would need at least 300-400 genes for a cell to function. And that's already quite complicated to have 300-400 genes to work together so that the cell is functional.
So how many base pairs is that?
Sorry, a gene is approximately 1,000 base pairs, so it's 400,000 base pairs.
So a cyanobacteria is about what, 10 to 100,000
they are about
base pairs?
4 million or so. It differs. I think the largest genomes is about 8 million. Bacteria.
Yeah. Okay, so wait a minute. Well, hold on now. So you got these the simplest form that you're describing to me of life is actually not very simple. You're saying it's quite complicated. And
it is, yeah.
So let me ask you a question that I love asking astrobiologists. I've asked this several times before. You've got an environment where all of the building blocks of life are there. Okay, amino acids, all the possibilities that life can form are in existence. And so they're sitting there, they're not alive, the constituents of these components are not alive. How do you go from this primordial ooze that isn't alive, to something that is alive? Because apparently it's a big step.
I don't know. I have no idea.
It's a miracle, Tony.
Yeah, maybe not a miracle. But we have no explanation.
Well, there are a whole bunch of miracles that you have to. How do you get vesicles? How do you get how to get cell boundaries? How do you get
a drinking game? How many times was Jeff going to say miracle in a hangout? And every time Jeff says miracle,
I mean it in a different way, not a religious miracle.
Oh, now you're going to qualify it.
It is very. There are. I mean, there's a famous experiment that was done by Louis Pasteur.
Oh, I thought you were going to say Urian Miller. Okay, go ahead.
Yeah, he's a French chemist who started microbiology
right
in 1830, 40, 50. And he did a very famous experiment with this spontaneous generation experiment, where he showed that life cannot originate spontaneously, at least not in the type of vessels that he used for the experiment. It was an important experiment at the time, because there were a lot of theories out that life just could arise anytime.
Well, I think
everywhere.
those theories are still around, aren't they? I mean, people still think that we go
and
from this ooze to a simple life form that can
and
respirate.
We can never really disprove it, if it's happening or not, because probably if this life, if there's a generation of new life, it's probably not competitive. I mean, when life started, there was no life there to begin with, so there were no predators. It was a different type of environment, and you could imagine that it arose many times, but that there's only one life form that ended up with being the dominating ones, and that's the life form that connects us all. So we're all in family. If we compare the machinery of bacteria, of eukaryotes, of complex life, of more simple life, as you said, it's all the same. It's all related.
Although it is true that the oldest life forms, the successful ones, are still around. Maybe without, there are prokaryotes and eukaryotes that have survived even in the presence of more advanced life forms, right?
Yeah, but they have also been evolving for 4 billion years.
Sure, but they've occupied a niche. I'm imagining now, again, this argument that there's a niche that hasn't been filled yet, and there's a biological accident that allows hydrogen peroxide chemistry to work at temperatures that are much lower than the current biology. So miracles, unlikely accidents do happen that might allow some new primitive life form to fill that other niche, right?
Yeah, but when we compare life, all the life forms that we have studied, they work along the same principles. We can make phylogenies, and we can make phylogenetic trees, and they all point to one common ancestor. It's not so that you have several types of genesis in parallels. When we take archaea and we take bacteria, which are quite different in many respects, and we take eukarya and compare their genes and their genomes, they all point towards the same origin.
Which is fascinating, right? Because I think at some level the arguments for panspermia are even stronger if that's really true. But if there was a niche that wasn't filled up, and if we wait long enough, we might see the same process fill that niche. What you're describing, I think, is that you have to have competition in order to end up culling whatever happens, so that those evolutionary tracks get wiped out.
But I would say it's more likely that this niche will be filled out by life that already is there, just evolving into the niche, than new life.
Well, if it has the right chemistry, but if it's a different amino acid set, for example, or a different chemistry that allows the same basis for life, information transfer, whatever it is, don't you think that's possible?
I mean, you can never. Of course, it could be possible. I would say that a new life that is arising has no. It's not compatible.
It's at a disadvantage, isn't it?
Yes, it's not good enough, because what we have already has been evolving for so many years, adapting to the conditions, also forming the conditions to a large extent. So I think it's very likely that it would just be used as a substrate.
Now, I want to remind everybody that we've actually had this great discussion, very similar to this, a few months ago, earlier this year, and we had a guest on who was telling us about these protein folding loops that can actually be a mechanism for making life from nothing.
Prions, you mean?
What did I? Oh, sorry. So yes, and they are, and that's I don't have the Hangout hand. Do you know what it was, Kevin? Or Kevin, off the top of your head? You might want to put a link to that in the in the chat room, just so people can go back to that Hangout. It was amazing. It was the guy. He had a really good mechanism for answering my question of how we go from nothing to something.
Okay.
And
I have to watch that one.
Yeah. It was. I'm sorry. I just remembered.
David Deemer, I think
that was him.
David,
David Deemer, and he. Are you familiar with his work, Kai?
Yeah, I know him. I've read some of his.
Okay, good. So yeah, and he had a really good diagram and explanation. So go back and check that hangout,
Yeah.
folks, if you did not see it yet. Galaxia is commenting, Jeff, that she knows what you mean when you say miracles. I don't know what you mean. What do you mean when you say miracle?
Well, I mean, Kai comment too, but I think that in order to get life, there have been a series of very unlikely events, which people use to argue that, well, the great filter, right? We have this
That's
conversation.
Right. We talked about that many, many times. We're going to talk about it
many,
again
many
in a minute.
times. Okay, but there are so many unlikely events. What it really means is that we just don't understand the probability calculation, I think, that leads first to something like RNA, and then the sort of, I mean, life formed in a way that probabilities, I mean, maybe it formed on the surface of rocks or the surface of but somehow the just the unlikeliness of several events over the course of billions of years look like they're so unlikely they're miracles. But in fact, what it probably means is that we don't really yet understand the statistics.
Okay, but you know, that's such a charged word when you use it. And
Well,
okay, so yeah, something that's highly unlikely. It's better to just say it was highly unlikely. But yeah, when you say things like miracles, it makes me think, well, this is something outside of science. This is something that happens in some other realm. And so
I'd be interested in hearing Kai's take on whether. So one of the I think it's been argued down, but years ago, Sharif and Gordon argued that there's a sort of a Moore's law for biological complexity, that as you go back in time, on average, the number of information units that are transferred from one generation to the other, which is DNA, the number of base pairs in the DNA of creatures, has more or less increased. And if you follow that trend backwards to this sort of Luca sort of lowest life common ancestor, had to be more than, based on this scaling, more than 5 billion years ago, which some people used as an argument for, well, life has been spread throughout the galaxy via comets and asteroids in the form of water bears, or what do we call those multicellular creatures that seem to live?
Yeah, tardigrades. Yeah,
tardigrades, right?
Yeah.
So
what one should not forget with microorganisms is that you have these you have this vertical evolution from one generation to the other. But what is very common among bacteria is that you have horizontal transfer of genes. So, right. I mean, that would only work if you had only vertical processes, because then you would put one gene on top of the other and so on. But if you have the possibility of acquiring genes from your neighbor, which had made it, and they don't need to be related. I mean, they can, and it's known that there are whole pathways that have been transformed, have been given from one evolutionary line to the other. You cannot really do these calculations anymore.
Yeah.
I mean, also when you look into the eukaryotes, they have been acquiring organelles like mitochondria and chloroplasts, and these chloroplasts had an enormous influence, or mitochondria had an enormous influence on the evolution of the hosting cell. So genes have been passed, and it's very difficult just to make these calculations if you don't know how evolution functions and how organisms acquire properties from the environment.
Yeah. Okay, let me get to some questions. We're running out of time. Philip W., question for the panel. Would planetary protection come into play if we sterilize parts for a rover and then shipped it to Mars and had another robotic creation assemble it? So I guess we start with something that is sterilized, send it to Mars, and then have it build something that would be tailored to going maybe into one of these off-limit areas. What do you guys think?
I'm not into all the regulations. I don't know if it would be. For me, it would be perfectly acceptable.
Okay. Galaxia, could there be life in the water deep in the Earth? The water reserves that were discovered a couple of years ago.
Yeah, of course.
Okay.
I mean, there's only one limit, and this is temperature.
Just temperature. Okay, that's interesting.
There are plenty of nutrients and organisms. They can extract energy from any redox process that's going on. So I would say yes.
Raymond Connick, the density of Mars is so low, I wonder if human settlement is sustainable with just 30% the weight. Any thoughts on sending people there in the long term?
Yeah, they would have they would have many problems when they return, because their muscles and their body mass had reduced, their muscles have been reduced, their bones get less sturdy as they should be to support life on Earth. So that's a major problem. Apart from all the other problems.
Did you see the National Geographic sort of fictional rendition of colonization of Mars? I think it's a year or two ago.
No.
Oh, it's fabulous. It's a sort of interview of it takes place in the present and then decades away from now, and it was done by some of the same people that did the that Hollywood movie about the Martian,
yeah.
Right? But it was and they did it as a series. It went over many hours, and I thought it was spectacular. Sorry, I don't remember the name of it.
I'd heard good things about it too. I didn't get a chance to see it myself either. Andrew Planet, if we ever find life on Mars, will that give more weight to the theory that life on Earth was seeded by organic compounds from outer space in a sort of life-giving polymer panspermia?
Yes. If it has the same DNA, suppose it uses the same DNA complement, what would you think? I'm sorry, the same amino acid base pair.
I mean, if the easiest thing would be just to sequence it and to put it in our phylogenetic tree and see whether it fits or not.
Yeah.
If it points towards the same origin, fine. Then we have the same origin.
Alexis Desplin is asking, they have found moon rocks and Mars rocks on Earth. Have they ever found Earth rocks on either the moon or Mars?
Not that I know of.
Yeah, it's kind of hard to go the other way because...
wait, there was this claim, right? Remember years ago that I went the other way around, right? No, it was a Martian rock that
landed on Earth.
Confused.
Yeah.
It was landed on Earth, and the claim was that it showed microscopic evidence of life.
Yeah, this is the meteorite.
Right, but that was from Mars to Earth, and I think it's because we're in the gravity well of the sun on this side of it that it's easier to get stuff from Mars than it is for us to throw it out to...
Exactly.
Yeah, but that was finally argued not to be evidence of life.
That's right.
On Mars, right?
That's right. Yes, it was. Let's see. Andrew Planet, if the amphoteric nature of water itself... Is the amphoteric nature of water itself the most basic stage of life because of all the whole electrochemical potential it has? Is life water in stardust context?
Okay.
Did you understand that question? I don't know what amphoteric nature of water means.
I mean, water is a fantastic molecule because it helps structuring molecules to form lipids just spontaneously. On the other hand, water is a terrible molecule because it's really difficult to polymerize stuff in water. So when you look into polymerization reactions, when we're forming larger molecules, taking amino acids and making proteins, or taking nucleotides and making DNA, when you look into the enzymes that are catalyzing these reactions, what they need to do is to get rid of water, because the natural tendency for water is to split things rather than to allow to build things.
One of the miracles.
Special adaptations to form complex molecules.
One of the miracles. As
they would rather, for them to form, you need dry conditions, the absence of water. Okay. So it's complicated, but it seems, at least for all life that exists on Earth, water is essential.
Right.
All processes are chemical processes in the cells are in an aqueous phase. So this is also because of these amphoteric nature of water, that it has both and particularly the amphophilic properties of lipids that have both a
Okay, you're
water.
gonna have to tell me what amphoteric means. I don't know what
Is that
that means.
is that the same thing as polar, electronegative?
Yeah, water is polar. Yeah.
But is that what amphoteric means?
I must admit that I was thinking of amphiphilic. That's what I had in mind. Amphiphilic means that's when we look into lipids. We have one part that is water loving and the other part that hates water.
Okay, that's a good question, Andrew. Good one. Okay, Cello Fingers had a comment, Jeff, based on what you just said. The Martian meteorite ALH 84001, which is what you were referring to, although billions of years old, proved somewhat that there was life on Mars. That was the one that you were talking about, I think. The one that we thought had some evidence.
Yeah, so there's a whole bunch of controversy, but I thought Kai, I think, said it, that I think eventually the scientific community said, nah.
Yeah. Okay, so upscale electronics. Even if Mars is geologically dead now, shouldn't it still retain a lot of radiant heat? If nothing else, the gravity alone should create some heat, right? I guess he's talking about under the soil, maybe.
Yeah, that's true. It's not the heat capacity of Mars is such that to cool to the temperature of space or the thermodynamic temperature of the surface, the radiation will take a long time.
Mm-hmm.
I don't know what that number is, but you know, Kai?
How long it would take to cool? Or
it just given gravitational collapse and the fact that you reach some point where it's not actually converting gravitational energy into thermal energy. That's a long time.
I mean, as far as I know, the most important energy source is radioactive decay.
For a planet like Mars, that's probably true, right?
So that gives the most of the energy for the heating.
In the case of the Earth, it's sort of half and half, isn't it?
I don't know.
Yeah, but that's a good point to that question, which is the radioactive heating.
Okay.
And the Earth aluminum 26 and other good stuff.
Okay, a couple more. I'm sorry, I just want to get through as many as I can. David Corvin is commenting that season 2 is being filmed, Jeff. So there you go.
Excellent.
Nat Geo.
Can't wait.
And there was another one on the lower limit. I'm sorry, here it is. Juan Astorga Wells is asking, is there a lower limit to the temperature for life to emerge? What about organic solvent? So you've already said 150 or so degrees, too hot for life. Is there a lower limit?
As far as I know, there's people did some studies to investigate that, and as far as I remember, the lowest temperature where they could measure metabolic activity was at minus 40 Celsius.
Whoa! How does that work?
I don't know. I think it was. I think what they did, they took permafrost samples and they incubated them with radio-labeled compounds, and just waited for radio-labeled CO2 to be produced. And it was a very, very low activity, but apparently there's enough liquid water in veins so that if microbes stay in there, they can apparently still metabolize the organic compound.
Okay, one last question, upscale electronics. Could Mars actually have a magnetic field and currently experiencing a shift in magnetic poles? The Earth does that, but we still have a magnetic field even though it's shifting poles. So what do you guys say?
Yes, as far as I know, it doesn't have a magnetic field anymore.
And you need there's no dynamo on Mars, right?
But I think they saw the same as on Earth, that the poles had shifted. They can see that when they investigate iron-containing minerals.
Mm-hmm. So,
but that was a long time ago. I think that once convection in the interior stops, you can't have a dynamo, and the field just goes away.
Yeah.
Okay, we got about 4 minutes left, and I want to ask this question. I want to get into. There was Nick Bostrom is a writer I follow quite a bit, and he wrote a good paper on why he hopes we don't find life on Mars. And we've talked about great filters here before. Great filters are these things that a species or a planet or a biosystem might encounter that would prevent life from getting past a certain point. A great filter might be the fact that life itself is hard to form. That may be a great filter that prevents life from permeating the universe. Another idea of a great filter for why we haven't seen civilizations is that maybe civilizations reach a certain point and they destroy themselves or whatever. And so that would be a great filter. I subscribe to the theory or the idea so far anyway, and all these hangouts that I've been doing, is that the step that goes from no life to life is a really, really, really hard one. It doesn't happen very often. And I don't think, and I think because of that, life isn't so ubiquitous as we would hope that it is. Now, I'd like to get your thoughts on this. If we find life on Mars, then and then we find that it is not, that it is independent, that it did not form from Earth, that it wasn't a panspermia thing, didn't come from Earth and land on Mars, but that if it was independent and actually began on the planet Mars, my contention is that that's a bad thing. Because that means that in the same solar system, on two separate independent occasions, life arose on its own, which means that life is everywhere. If we find it on Mars, life is everywhere. That's what I've always said. What do you think about that? And do you agree that finding life on Mars would be a bad thing for us? Because it means that we've already it means that the great filter is probably still ahead of us. The great filter is not in our past, it's in our future.
I can't see why it should be bad finding life on Mars. I would find it extremely exciting.
Okay.
And that would allow us to study the evolution of life in a much broader context.
Do you agree with the statement that it would probably mean that life is everywhere? If in the same solar system, life arose independently twice.
Already the fact that we find life on one planet in our solar system tells you that, we have no clue how difficult it is to make life.
That's right. And we also don't know how ubiquitous it is. It says nothing about how common
we just
life
know
is.
From Earth that the oldest rocks that we investigate already have life in them. At least that's what the signatures tell us. So it must have been there right from the start.
But that goes back to Jeff's point that once life begins, it's quite tenacious, that we don't give it credit for being robust. Well, we know that once it exists, once it forms, you have a heck of a time killing it off.
Yeah, it didn't really succeed on Earth in more than 4 billion years. We had a lot of incidents that could have sterilized the surface of the Earth, but
so it's not going to bother you that this great filter is probably in our future then.
Yeah, I don't really see that point. Why? What is?
Okay, all right. Imagine that there is that. First of all, we got to start with the assumption we don't see life elsewhere very often. We haven't come across it yet. Jeff and I have argued about this.
But wait a minute. It's because we can't. We don't. We're just on the verge technologically of being able to see that life.
Okay, all right.
So
sure.
Even if you take Earth, there was a long period of time where you couldn't have found life on Earth from with remote sensing. Life. The most important waste product that would tell other civilizations that there could be life on Earth is oxygen.
I will say that the only thing that lets me sleep at night is the fact that Jeff's right. We haven't really started looking. We haven't really started looking all that much for life in the universe. We've only.
But the problem is also, how can we identify it?
Yeah, I agree, and I hear that. But
the good thing with Mars is that we can go there, so we can take samples, we can investigate them. But if we take extrasolar planets, they are so far away that there's no way to go there. So that you need to have a signal that is sufficiently strong and
heat signature.
That's right. We talked about that last hangout. That's correct.
All
right. Okay. Well, so you're just hoping no matter what we find. What about you, Jeff?
You know what I think.
I know.
I feel like I'm an extremophile. I just it's this sort of.
You are an extremophile.
That we don't know what we don't know, and it is true that it's an extremely unlikely event that somehow life emerges. But I think to get to where we are now, it was 6 or 7 extremely unlikely events. So faced with the need for one miracle, when in fact 6 or 7 miracles happen. And one miracle would have made it such that, if I believe some of the calculations, that there's one planet in the galaxy that has life. But now you have 6 or 7 of those miracles, and there's still only just one planet? Or is it that we just didn't understand how we didn't know how to do the calculation for the statistics of that? Either that, or once life ever emerged, as unlikely as it is, it spreads, and we're part of this sort of galactic ecology. That there really is an ecology defined by solar systems and planets, and the tardigrades or the UV resistant cyanobacteria or the prions or whatever it is that end up being able to migrate via comets and passing asteroids is good enough to get through your great filter. I guess I'm.
Thank you. I can go to sleep now tonight. Thank you. I appreciate it. All right. So to me, it's the jury's still out on this. I mean, I'm glad that we are exploring these topics, and I really hope beyond all hope that we are able to, with Planets.life, for example, the Planets Foundation, the efforts that these guys are doing, shed a lot more light on this, because we have only just begun to look. Okay, I'm going to have to stop the hangout there. We are out of time. I want to thank my guest, Dr. Kai Finster he's an astrobiologist from Aarhus University in Denmark. Thank you for staying up so late and talking to us, Kai.
Yeah, it was a
This
pleasure.
has been a lot of fun. And we will be back in 2 weeks. Kevin, do you want to talk about what we're going to be doing, or is it too early yet?
A little too early, but I did want to talk about our Kickstarter that we still
by all means, go right ahead.
Actively have. So we're currently fundraising on Kickstarter to build a prototype of a brand new type of telescope mirror to be used in large telescopes to specifically image exoplanets, to image oceans and continents. And Jeff and the colleagues at the Planets Foundation have been doing a lot of good work to design this new type of telescope mirror. So current large telescopes like the Keck or GMT, they're really large, thick mirrors. You have to abrasively polish them. It takes a lot of time. It costs a lot of money. And then as the mirror's moving around, you have decent sized actuators on the back that are correcting the mirror as it moves. So with this prototype, it's completely new. Jeff can probably talk a little bit better about it than me, but it takes really thin window glass, fire polished window glass, and then we 3D print polymers on the back of this window glass. You can think of a polymer as a synthetic muscle. And essentially it's just a way to make incredibly lightweight, thin telescope mirrors to create telescopes like the ExoLife Finder telescope that we're working on.
And and your Kickstarter has been going on, and it's going quite well from what you told me yesterday. So.
Yeah, we're about 90%. We have 3 days left.
How do they get there? How do they get there? Kickstarter.
Just Kickstarter.com and search ExoLife Finder, and it'll pop right up.
Great. So definitely go there and check out and support these guys, because the work they're doing is hugely important, especially so that I can sleep at night and find, get this life found, so we can get a handle on this thing once and for all. What is that?
These are some of the gifts and rewards that you can get when you back us. So this is the ExoLife Finder telescope. It changes colors. We also have...
Wait, keep holding it up. I'm making you big. Okay, let me get rid of all this stuff. There you go.
So this is a model of the ExoLife Finder telescope that Jeff has designed. And it's just...
That's really cool, Jeff.
Yeah.
I like the colors.
Okay, great. Thank you very much.
But he's got a tardigrade, right?
Yes, I do. Hang on. 1 second. All right.
Is a tardigrade different than a water bear?
It's the same.
There it goes.
I think they're creepy looking, the tardigrades.
Oh, yeah.
They kind of look like a cross between a manatee and something scary, but
it's scary, definitely scary.
Yeah.
And that could be our ancestor.
Awesome. So those are some of the gifts that you get if you participate in the Kickstarter campaign. So please go there, folks, and contribute. All right. Well, that is it for this week. We will be back in 2 weeks. We're putting together the topics now. The best way to find out about future hangouts is go to deepastronomy.com/hangouts or deepastronomy.space/hangouts, and I have a calendar there. As soon as it's finalized, I put the events in there as they are completed. So that's the best way you can find out. So thank you all so much for watching, and as always, keep looking up.